Hello, this is Jordan.
And this is Quinn.
Yeah, so I am coming to you straight from the cab of my pickup today, parked out in a North Dakota bee yard. The wind's howling a bit out there, but the heater's running in here, so we're good to go.
Nice and warm in the truck, I imagine.
Oh, absolutely. And, most people look at a jar of honey sitting on their kitchen counter and they just see, well, a sweetener, like something you stir into your tea when you have a cold or drizzle on a biscuit.
Right, just a pantry staple.
Exactly. But sitting out here looking through the windshield at a couple thousand colonies, I see something completely different. When you really understand what's happening inside those wooden boxes, you realize you're looking at a highly engineered pharmaceutical-grade substance.
Which really makes this the perfect conversation for us to have today. Because, I brought a rather large stack of clinical dermatology papers, apiology data, and some historical records with me. We're going to bridge two worlds that might seem totally disconnected if you're just casually observing.
Yeah, they seem worlds apart.
Exactly. Yeah. On one hand, you have your reality, the mud on the boots, weather-beaten reality of managing thousands of bee colonies out there in the elements.
Getting stung and dealing with the wind, yeah.
Right. And on the other hand, you have the highly sterile, high-tech, strictly regulated world of clinical dermatology and advanced wound care.
And that's our whole mission today. We're going to walk you through the biological math happening inside the hive, how ancient civilizations recognized and utilized that math long before they had microscopes, and how modern medicine is finally proving exactly why it works.
It's a fascinating timeline.
It really is. And I'll tell you right now, I heavily rely on live digital dashboards to track this data for my own operation. By the time we wrap up, I want you to feel motivated to go check out some of these live apiary dashboards for yourself.
Because the numbers are staggering.
Oh, they're wild. Because to understand how honey can literally heal a severe diabetic foot ulcer, you first have to understand the brutal, unforgiving economics of how bees gather nectar in the first place.
It really is a matter of brutal economics. And it's all governed by strict physical constraints. A forager bee is essentially a tiny, highly calibrated flying machine, and her operating parameters are incredibly narrow. Let's just look at temperature, for example. The ambient temperature floor for takeoff is 55 degrees Fahrenheit.
Yeah, I see that threshold play out every single spring. But, mechanically, why 55 degrees specifically? What physically stops them from flying at 50 degrees?
Well, it comes down to internal heat generation. Below 55 degrees, her thoracic slight muscles simply can't vibrate fast enough.
They just freeze up.
Basically, yeah.
Yeah.
A bee doesn't just flap her wings. She has to rapidly contract and relax those thoracic muscles to create a high-frequency vibration.
Right.
That requires a massive amount of chemical energy to be converted into heat. If the ambient air is too cold, the heat dissipates faster than she can generate it, the muscles stiffen up, and she's grounded.
That makes sense. But honestly, out here, even if the sun comes out and it warms up, the real killer is the wind.
Oh, absolutely. Environmental turbulence is a massive energetic tax. When wind speeds hit about 12 miles per hour, a bee is forced to physically extend her hind legs mid-flight.
Just to maintain roll stability. I've actually watched them do that coming into the landing boards. They drop their legs like little landing gear.
Yes. But doing that completely ruins their aerodynamics.
It has to, right? It's like dragging an anchor in the air.
Completely. That tiny behavioral shift, just dropping the legs into the airstream, increases her body drag by 30%.
Wow.
So if she's flying into a 15-mile-per-hour headwind, that single flight is costing her 500% more energy than if she were flying in a gentle 5-mile-per-hour breeze.
See, this is where the practical commercial beekeeping reality hits hard. I always compare my foragers to a fleet of commercial semi-trucks.
That's a great way to visualize it.
Yeah, because if I'm running a logistics company, I'm constantly calculating fuel efficiency versus payload. Every mile driven costs diesel. Well, a worker bee is literally a flying fuel tank.
She is. She burns about 11 milligrams of honey per hour just to keep herself airborne.
Yep. And a really good heavy payload of nectar is only about 40 milligrams.
So the margins are tiny.
Razor thin. So she's doing the math before she even leaves the landing board. If she calculates that she's going to burn more calories fighting a 15-mile-per-hour wind than she's going to bring back in her honey stomach, the math fails.
The return on investment is negative.
Exactly. When that happens, the colony makes a collective decision to just stay home and conserve resources. I sit in my truck and watch this happen, and I can't just guess what's going on out there. I rely on live dashboard metrics to know exactly what kind of environmental resistance my thousands of colonies are dealing with at any given hour.
And that biological math gets even more complex when you look at how they actually navigate to those flower patches and back.
Oh, navigation is crazy.
It's not just visual landmarks. Honeybees use the sky's polarized light as a celestial compass.
Right.
Beyond that, they have microscopic magnetite crystals in their abdomens that literally align with the Earth's magnetic field.
Wait, hold on. You're saying they have built-in magnetic compasses?
They do. It allows them to navigate and find their way home, even when heavy, dark cloud cover rolls in and obscures the sun.
Okay, but if they're relying on the magnetic field of the Earth, doesn't that make them vulnerable to atmospheric interference?
It absolutely does, and this is where the research gets fascinating. They are incredibly vulnerable to space weather.
Space weather.
Yeah. When there's a significant solar flare on the sun, it triggers geomagnetic storms in our atmosphere. We measure the severity of these storms using something called the KP index, which is a scale from 0 to 9.
Okay.
If that index spikes to a 7 or higher, it creates a massive amount of magnetic static in the atmosphere.
I need to stop you there. Are you telling me a solar flare millions of miles away can ground my bees in a clover field in North Dakota? How does that actually work mechanically?
I know it sounds like science fiction, but yes. When that KP index hits a 7, the severe fluctuations in the Earth's magnetic field physically overwhelm the sensitivity of those tiny magnetite crystals in the bee's abdomen.
Oh, wow.
The compass gets permanently scrambled. So the forager gets out into the field, the magnetic signal gets noisy, she loses her orientation, and she literally gets lost.
Yeah.
She'll fly in circles until she dies of exhaustion because she cannot locate the hive.
That is just wild. The scale of that, from the sun down to a quarter-inch insect, is hard to wrap your head around.
It's a delicate system.
It really is.
Yeah.
But, okay, let's say our forager navigates the wind, she beats the solar static, and she gets that 40-milligram payload of raw nectar back to the wooden box.
The mission still isn't over.
Not even close. Getting it to the hive is only half the battle.
Yeah.
Once the field bees hand off the nectar to the house bees inside, the factory floor takes over. And the physics of the local weather completely dictate whether that nectar turns into stable honey or ferments into a massive toxic problem for the whole colony.
Because once it's inside, it becomes a race against microbiology. Raw nectar comes into the hive at roughly 70% moisture. If it stays at that moisture level, osmophilic yeasts are going to have a field day.
We should probably define osmophilic for a second.
Good call. Osmophilic yeasts are microorganisms specifically adapted to survive in environments with high osmotic pressure, meaning high sugar concentrations.
Okay, got it.
Normal yeast would die in nectar, but osmophilic yeast thrives in it. If they're allowed to multiply, they'll rapidly ferment the nectar, producing alcohol and carbon dioxide, completely ruining the colony's winter food supply.
Which is a death sentence for the hive.
Exactly. To stop this, the house bees have to fan that nectar down to under 18% moisture. At that specific threshold, the water activity drops so low that those yeasts simply can't survive. The honey becomes microbiologically stable.
Right.
But here's the catch. The efficiency of that curing process depends entirely on the vapor pressure deficit of the outside air.
I deal with this every August. The humidity gets sticky here and the bees just seem to stall out. You walk the yard and the boxes sound like jet engines from all the fanning. But break down vapor pressure deficit for us.
Sure. Vapor pressure deficit, or VPD, is essentially the difference between the amount of moisture currently in the air and how much moisture the air can physically hold when it's totally saturated. Think of the air like a sponge.
Okay, cracking.
If the ambient humidity is sitting at 90%, that sponge is almost completely full. The VPD is very low. So when the house bees are trying to evaporate water out of the nectar, the outside air simply won't accept the moisture.
The gradient is terrible.
Right. It becomes physically exhausting for the house bees. They have to form long chains at the entrance and fan their wings continuously just to mechanically push the heavy, wet air out of the hive.
Which consumes massive amounts of energy. They're literally eating the honey just to have the energy to fan the water out of the nectar. It's a vicious cycle.
It really is a treadmill.
And as a commercial guide, this is where my specific interventions come into play. A lot of people think picking a breed of bee is just a hobbyist detail, like picking a color for your truck.
It's so much more than that.
Oh, it is. Genetics play directly into this survival math. It's how we prevent massive colony loss in the winter. Take the Italian bee, for example. It's the most common commercial breed in the world.
Very popular.
Incredible honey producers, but genetically, they evolved in the temperate Mediterranean. They have almost zero cold offset. If the temperature drops, they freeze up and shut down. But compare that to Russian bees. They evolved in the Primorsky Krai region of Russia, where winters regularly hit -40 degrees.
How does that actually translate to their biology, though? How do they survive when the Italian bees die?
It's a combination of behavior and physical traits. Russian bees form much tighter winter clusters to conserve heat. They lower their metabolic rate earlier in the season based on day length, and they actually have thicker cuticular hairs.
Oh, they have a thicker coat.
Exactly. All of this gives them an 8-degree Fahrenheit cold tolerance offset. They will actively fly and forage in weather that would freeze an Italian bee solid.
Wow, 8 degrees is huge in that context.
It changes my entire timeline for spring buildup. It dictates exactly when I need to intervene and add pollen sub, which is a protein supplement, to keep the brood alive before the natural pollen blooms. And by the way, you can find more info about what we are talking about at Manuka Wound Science by visiting manukawoundscience.org. I highly recommend you go there and look at the live Hive Ops Center data for yourself. You can actually see these wind, humidity, and temperature thresholds calculating in real time.
It's an incredible visual resource because it takes the invisible forces shaping the hive and puts them right on a screen. Now, obviously, we use digital sensors and satellite data to track this ecological precision today, but human beings have been successfully exploiting these exact bee mechanics for over 10,000 years. We didn't just stumble into this relationship recently.
No, we've basically been running a 10,000-year siege on the hive. We've been trying to master their system for millennia.
Exactly. If we look at the historical records I brought, the earliest physical evidence we have is a rock painting at Cueva de la Araña, the spider cave in Valencia, Spain. It's dated to about 10,000 years ago.
What does it show?
It shows a human figure clinging to ropes, reaching into a cliff face cavity to harvest honeycomb, with a collection basket hanging below. What's crucial to understand here is that this is not an image of a desperate, hungry scavenger stumbling upon a feral hive.
Right, it's not an accident.
No, it depicts deliberate engineered technique, rope making, container craft, calculated risk. It shows an established tradition. Fast forward to dynastic Egypt, and it becomes fully state-administered apiculture.
Wow.
The Ebers Papyrus, dating to roughly 1550 BCE, is one of humanity's oldest surviving medical texts. Out of its 877 remedies, over 500 of them are heavily honey-based formulations. They were prescribing it for severe burns, deep lacerations, and even eye diseases.
And they were doing that because they saw the clinical outcomes. They didn't have microscopes. They couldn't see the molecules doing the work, but they saw the tissue healing. You see this deep, almost technical understanding of the bee's environment in ancient texts, too. Think about the biblical concept of a land flowing with milk and honey. People read that today and they just hear vague poetry about wealth or a nice place to live.
Right, a metaphor.
But to a practical agriculturist, to someone who manages land for a living, that phrase is a highly precise ecological checklist.
A checklist. I've never heard it described as a checklist. Unpack that a bit.
Well, think about what those two specific things require to exist simultaneously. Milk requires managed livestock grazing on sustained, healthy pasture.
Okay, yeah.
Honey requires diverse, nectar-producing flora and stable pollinator populations. If you overgraze your livestock, the cows eat all the blooming plants and the bees starve.
This system breaks down.
Right. And if you don't have healthy soil and proper seasonal rain, you get no pasture for the cows and no nectar for the bees. To say a piece of land is flowing with both milk and honey means you're looking at an environment in absolute perfect ecological balance.
That's fascinating.
It means the stewardship of the land is flawless, allowing both heavy agriculture and sensitive apiculture to thrive simultaneously without one collapsing the other. It's not poetry, it's a technical assessment of soil health and weather patterns.
That makes perfect sense. The ancients clearly understood the environmental requirements, and they definitively understood the medical applications, as we saw in the Ebers Papyrus. They knew perfectly well that honey worked for wound healing.
Yep.
But as you pointed out, they didn't have the molecular science to explain the how or the why. And modern clinical hospitals don't operate on ancient folklore. They demand peer-reviewed proof.
Right, which bridges us from ancient history directly into modern clinical dermatology. I see the research papers you have there. What was the actual turning point where the medical community finally looked at the data and said, okay, this isn't just an old wives' tale, there's serious measurable chemistry happening here?
It happened in the late 20th century. Professor Peter Molin in New Zealand, and later, researcher Thomas Henle in Germany, made a landmark discovery regarding one specific varietal, Manuka honey. For a long time, scientists knew normal honey had mild antibacterial properties.
Mostly due to the low water content we talked about and trace amounts of hydrogen peroxide, right?
Correct. When the bees add an enzyme called glucose oxidase to the nectar, it produces small amounts of hydrogen peroxide, which cleans the honey.
Right.
But Manuka honey was doing something entirely different. The researchers discovered a bioactive compound called methylglyoxal, or MGO. This is a non-peroxide antimicrobial compound that is astonishingly powerful. It actively destroys bacterial biofilms. We're talking about a documented 95.2% kill rate against MRSA, which is a notoriously drug-resistant staph infection that plagues modern surgical wards.
Let's make sure we define a biofilm, because that is the real enemy in wound care. A biofilm is basically a microscopic fortress that bacteria build around themselves in a chronic wound, like a diabetic ulcer.
Yeah.
Standard antibiotics often just bounce right off the walls of that fortress.
Right, because the bacteria secrete a slimy extracellular matrix made of sugars and proteins that physically shields them from our immune system and from traditional drugs. But the MGO in Manuka honey doesn't just bounce off.
Because it's so small.
Yes, because the MGO molecule is so remarkably small, it slips right through that slimy matrix. Once it gets inside the fortress, it targets the bacteria's vital proteins and physically cross-links them.
It traps them.
It basically glues the bacteria's internal machinery together so they can't metabolize food or divide to reproduce. The infection just collapses. But here's the critical part. This isn't just a random chemical occurrence. It's an integrated biological system. It requires the specific nectar from the Leptospermum scoparium plant, the Manuka bush.
I've always wondered about the origin of the MGO. Is it in the plant or does the bee make it?
It's actually a collaboration. The raw nectar from the Manuka bush doesn't contain MGO. It contains a precursor compound called DHA, or dihydroxyacetone. The foragers gather that specific DHA-rich nectar, bring it back, and add their specific digestive enzymes to it. Then, during the maturation process inside the hive, which is maintained at a very warm 93 degrees Fahrenheit, that DHA slowly undergoes a chemical conversion over several months, transforming into the highly stable, highly potent MGO.
Unbelievable.
Plant chemistry, insect enzymes, and time working in perfect thermal concert to produce a targeted antibacterial agent.
It's unbelievable when you break the mechanism down like that. But this is where we have to translate the laboratory science into the practical bead-a-bandage reality. Because I think a lot of people hear this and think they can just go to the local grocery store, buy a plastic bear full of clover honey, and squeeze it onto an infected cut.
Which is incredibly dangerous.
Highly dangerous. In the clinical world, the numbers and the strict protocols matter immensely. We grade this medical honey based on that exact MGO concentration.
And the grading tiers are entirely what dictate the medical application. Can you break down those specific MGO thresholds for us?
Absolutely. So if you're looking at a jar with an MGO rating under 400, that's your daily functional use. That's for oral health, maybe soothing a sore throat, general wellness.
Routine stuff.
Right. It's great stuff, but it's well below the threshold for acute wound care. Once you hit MGO 400 and above, you're at the clinical entry point. That's where medical professionals start using it as an antimicrobial dressing base for primary wound care and minor burns.
Okay, that makes sense.
But then you have the absolute top-tier MGO 800 up to 1600. That is strictly pharmaceutical grade. Those reserves are deployed for recalcitrant biofilms, severe diabetic foot ulcers that aren't responding to antibiotics, and advanced post-surgical prophylaxis.
The real heavy hitters.
Exactly. And here's the reality check from the commercial beekeeping side producing MGO 1600 honey. Is incredibly difficult. You don't just scoop this out of a backyard hive. It requires strict aseptic apiary standards.
I imagine the quality control is intense.
It is. You have to use GPS-validated forage mapping to ensure your bees are only hitting dense Manuka blooms and not diluting the crop with other nectars. The extraction processing has to strictly mitigate heat variance so you don't destroy the active MGO compounds.
Right.
And finally, it requires non-irradiation sterilization methods to ensure you don't introduce any foreign spores or pathogens into a patient's open wound. It is a highly regulated, validated medical device by the time it reaches the hospital.
And honestly, that level of human precision and regulation is really just our best attempt to match the innate mathematical precision of the bees themselves.
They definitely had a head start.
They really did. Which brings me to a final thought I want to leave you with today. We've talked about the strict mathematics of their flight and the complex chemical engineering of their nectar processing and DHA conversion. But consider the physical architecture of the hive itself. Back in 1851, a man named Lorenzo Langstroth discovered what we now call the bee space. He realized that honeybees naturally, instinctually, leave a gap of exactly 9.5 millimeters between the surfaces of their comb.
I see it every time I pull a frame out here. If a space is even a millimeter smaller than that, they glue it shut with a sticky resin called propolis. If it's larger, they fill it with burr comb and wax.
Right, but at precisely 9.5 millimeters, they leave it open as a navigable passageway. They use this exact unvarying dimension to build perfectly tilted 13-degree hexagonal cells that optimize volume for honey storage while using the absolute minimum amount of wax secretion.
Which structural engineers will tell you is the most efficient shape possible in nature.
Exactly, and here's the kicker. They do not learn this measurement. A newly hatched worker bee doesn't have to be taught by older bees how to measure 9.5 millimeters or how to calculate a 13-degree tilt for fluid retention.
They just know it.
They are born knowing it. Its primary design coded directly into their biology. So the provocative question I want you to think about is this. If these tiny insects possess this level of innate, flawless architectural and chemical engineering, if they can automatically calculate wind drag, navigate by polarized light, and synthesize MRSA-destroying compounds through thermal enzyme conversion, what other microscopic miracles are happening inside that dark wooden box that we simply haven't built the tools to measure yet?
That is definitely something to chew on the next time you look out over a field of clover and see a worker bee landing on a flower. The complexity is just staggering. Well, before I put the truck in drive and get back to work out here, I want to remind you to visit ManukaWoundScience.org. And while you are there looking at the live ops data, I want to explicitly instruct you to look for other informative podcasts located on the various pages of the site to learn more about specific subjects, like the mechanics of biofilm destruction or the specific metrics behind the bee weather reports. Keep your eyes open, respect the science, and we'll catch you next time.